The next talk is given by Jingyuan soon. He will talk about brain encoding and decoding.
Does this work? Yeah, it works. Good afternoon, everyone. So I'm today going to give a talk about brain encoding and decoding for visual and language perception, which is just like a review of my work during my working with Professor Simons for the calculus project. So I'm first going to give an overview of my research interests, which drives my research. So my major research interest is to transfer insights through the alignment between brain and computational representation of language. I specifically use AI models to predict and decipher brain activities related with language processing, and I've been recently extending my work to visual area. So here, we can also use this to explain briefly what is neural encoding and what is neural decoding. So for neural encoding, it is just to use a model to predict how human brain will give new responses to outside stimuli, or how human brain will have such kind of neural responses and activities when they are processing when they are conducting a certain kind of function. Well, for decoding, it is to reconstruct from the brain activities to decode the stimuli that human is perceiving or the thing that is imagined by human brain. So how can we exactly use the AI models to build a connection between the representation learned by human brain and the representation learned by artificial neural networks? I will use my recent work accepted by IGCAI 2023 as an example to give an explanation. So on this work, we are going to compare or say correlate the representations learned by supervised large language models with human brain. What we are interested in is to see like how the text information that introduced by supervision may influence the encoding and decoding performances of these embeddings. So we know that there are two recently dominant methods for introducing supervised information to large language models, which is fine-tuning and prompt tuning. And they actually represent two different philosophies of introducing information from external source to the pre-trained knowledge of a large language model. We know that for fine-tuning, we will update the pre-trained weights to adapt to a specific task or target distribution. But for prompt tuning, we will generally freeze the pre-trained weights and learn additional parameters to adapt to the task that we are interested in. So they actually reflect two different kind of methodologies to introducing the task-related information. And what we are interested in is to say how these different kind of philosophies, which kind of this philosophy would be more similar to human brain's underlying mechanism when they are formalizing language representations. So how we started this question, we are just going to use the embeddings produced by the fine-tuned models and the prompt-tuned models and use these models to build regression-based neural decoders to decode the brain activities. So here we give a very brief introduction of what is prompt tuning and prefix tuning. And if you are interested in this work, you can refer to the paper. So for the prompt tuning method we are using the prefix tuning, which is a mutant of this direction, which is just used learn the embeddings, optimize the embeddings, and prepend the embeddings to the input of the transformer model, and keep the original weights of the transformer frozen. We just optimize the prefix to fit on a downstream task. For example, here, like a classification task. And after fine-tuning and prompt tuning, here is some details of how we optimize this, and I won't give too much details about that. And we are optimizing the task as the models on 8 tasks which involves wide range of cognitive linguistic skills. For example, emotional categorization and sentiment classification. After tuning on this task, we got both prompt-tuned embedings and fine-tuned embedings, and we use these embedings to build neural decoders. And here is the performance. We conduct research on 4 brain functional networks, including the brain language network, the semantic system, the default model network, and the vision network. So we can say that we can see a consistent advantage of prompt-tuned embeddings over the fine-tuned ones in all the 4 functional networks, especially in the brain language network. And we can also say that for the syntactic chunking task, which is work. So it doesn't seem to work. So we can see that on the chunking task, which is the second bar on the top left figure, we can see that the fine-tuning, the prompt tuning embedding significantly outperform the fine-tuned embeddings on the neural decoding accuracy. And such kind of finding is consistent among the 4 functional networks. And we also found that for the tasks that involves fine-grained modeling of semantic relation and conceptual relation. For this kind of text, we got embeddings that can better decode the brain activities, such as coreference resolution, word sense disambiguation, and named entity recognition. To prove the findings that we found, we go into specific regions within the brain functional networks. And here we see the x-axis. There are just some different regions within the brain language networks. And we here can see more clearly the advantage of prompt-tuned embeddings on all the regions within the brain language network. And we still also see the outperformance of the coreference and word sense disambiguation task over especially the syntactic chunking task. So here that may indicate that like deep level semantic information could be more involved in human brain's language representation when they are listening and trying to understand the sentences, potentially taking a larger proportion than the shallow syntactic information. And we also can come to such kind of conclusion that maybe the philosophy or say the mechanism taken by prompt tuning is more close to how human brains are formulating language representations. And because this is, in this study we conduct all the experiments on English speakers with when they are when they are reading sentences. So we are curious if such kind of findings may be consistent across other languages and other language processing modalities. So we shift the same kind of methodology to Chinese, native Chinese speakers, which listening to the language stimuli during the neural imaging collection, and we use different kind of methodology. But in this time, we are focusing on neural encoding, which we are building regression-based encoders to predict the human brain's neural responses to the external stimuli, external linguistic stimuli. And we are still using the prompt tuning and fine-tuning methods on 8 tasks. And we here found very similar patterns. This figure we show here they depict the significance of comparison between the prompt tuning and the fine-tuning's neural encoding accuracy, which is measured by Pearson correlation. And we can see here on the first line of this picture, especially the first 3, which are embeddings learned on the 2 text classification tasks and natural language inference tasks. We can see very significant and apparent advantage of the prompt tuning embeddings over the fine-tuning embeddings in predicting the brain activities within these areas. We can see very more yellow on these pictures indicate that on that area, the neural encoding performance of prompt tuning is more significantly higher than the fine-tuning. So we can see within larger regions of the brain language network, like the Broca area, fine-tuning is significantly beaten by prompt tuning embeddings. So the finding that we get in the English data with human subjects reading sentences it's reproducible in the Chinese study where we conduct on human subjects listening to podcasts. And here are my other related publications, because since my PhD and along my postdoc working with Professor Moens, we are trying to discussing the representation learned by artificial neural networks and the representation learned by human brain. And here are some kind of my related publications. If you are interested in this area, feel free to contact me, and we will be very happy to discuss related work in this area. At the beginning of this presentation, I also mentioned that I'm trying to extending my research beyond the language area, especially given the recently very rapid development of deep generative models, such as diffusion models. So this work is one example of my extension from the language area to the vision area. So in this work, we are doing neural decoding, and we are trying to reconstruct high-resolution images that are viewed by human subjects from their brain activities. So what we achieve this is we first learn denoise representations from fMRI with like contrastive learning, and we then use the trained fMRI encoder to get a diffusion model to generate the viewed images from brain activities. And because the time limit, I won't go into too much details of the methods. We can first have a look at the result. In this work, which we published last year in the NeuroRips, our model significantly outperform private SOTA methods by about 30% in as shown here, the 50-way top one classification method metric. And here we can also have a look at the results generated by our model. Like the hours here indicate the results is generated by our proposed algorithm, and GT indicates the ground truth, while other three columns indicate the results generated by other models. And DC-LDM is at that time the SOTA method. We can see that our method can generate more semantically consistent and plausible images. And here are more examples generated by our model, with the first line indicating the ground truth, while the second line are the results generated by our model. For example, like we can generate pretty semantically related content through the methods that we propose. Here is also some other examples, because we would like to show that here on different subjects, our model generate different results, because it is natural for us to know that different people with different educational backgrounds or different growth pattern, they have different understanding of their outside world. So it is also logical that even with the same kind of methodology, we may generate different kinds of results from these brain activities. Okay, that's all the brain coding and the decoding work that I would like to share with everyone. Thank you very much. Yeah, not actually. Actually, on some regions, specific regions, prompt tuning can even outperform the naive models. Yeah, but on most regions, the naive model is the best. Yeah.
So what's your explanation for that?
Oh, actually, we have a very recent work that is still under review. We discussed this problem, and we found in that work we are using the stimuli that is directly recorded, using to record the brain responses to tune the model, use prompt tuning and fine tuning. And in that work, we found that prompt tuning can still significantly outperform the naive models, the untrained models. So combining that result with these results, we indicate that the reason that the tuning methods leads to worse performance, decoding performance and encoding performance. One reason is that the target corpora that the model is tuned on may be not related to what human brain is conducting or trying to understanding at that time. And it may be in very large, there are very large gap between the corpora that we use to tune the models, between the actual corpora or the natural corpora human brain is using when they are learning language and understanding language. And I think that is one reason that no matter fine tuning or prompt tuning, they can, when we are adapting to something that is not related with human brains, some corpora that is not related, they will lead to general worse performances. That is one reason. And the second reason is that we also found, because in these two papers, there is a limitation that we only test with one prompt tuning method. And we also found that like different kind of prompt tuning method, like different kind of integrating the external knowledge to the pre-trained model, they actually have different kind of correlation with human brain. So the one thing to take away is that it's very important to strike a balance between the external knowledge to be integrated and the already have pre-trained knowledge. The more that we can strike a balance between these two things, the more we can expect better correlation with human brain.
Yeah, that's really interesting. I'm wondering, just one follow-up on this, about this. So you have these different tuned models for each kind of task. And are the performances on these tasks similar across the prompt tuning and the fine tuning study?
Oh yeah, so because yes indeed, we conduct hyperparameter research to guarantee that the task performance of prompt tuning and fine tuning, they are at a very close level. And we use such kind of models to do the study to, as a controlling variable.
Yeah, very nice.
Thank you for the question. Okay. Oh yes, this is a pretty not very complex thing, so I can use this to explain. So here, because we do not use very complex models to build a connection between the human brain and the embodies, we are just using regression models, ridge regression models. We train ridge regression models to predict from the brain activities, the fMRI there, to